Hey everybody, how's it going? I hope you're doing well. We've had a lot of weather since I've seen people last. Hopefully you're all safe, dry, and warm. Um, we're going to go over section 6.2 today. Again, a couple questions at the end of the section. Split it into two parts, just like I've been doing. Um, again, I'm working on getting caught up as I can. Grading tests and getting stuff looked at. We are home. We're happy. Everybody's healthy. We did have to spend a couple days in the hospital, but that was kind of expected. We couldn't have any visitors, just me and my wife and our new son, Roman. So that was kind of nice. Now we're home. We have our daughter, Tessa, who's almost 2. She's running around like a nut. She's not too happy about having a baby brother as of now, but we're working on it. And, we have the dog, Wesley. So we're just one big happy family now. So, section 6.2 transforming and combining random variables. Okay. So let's look through this real quick. Section 6.1, we looked at several examples of random variables and their probability distributions. We also saw that the mean, mu sub x, and standard deviation, sigma sub x, gives us important information about a random variable. So mean, standard deviation. Consider this setting, roulette wheel. Okay, a lot of times used in stats examples. An American roulette wheel has 38 slots on the wheel like this, number 1 through 36. They're the black and red ones split evenly. And then there's the 0 and the double 0, which are both green. So half the slots for 1 to 36 are red, half are black, both 0 and double 0 are green. Suppose that a player places a dollar bet on red. The ball lands in a red slot, the player gets their dollar back plus an extra dollar for winning the bet. If the ball lands in a different color, so the black or the green, the player loses a dollar. Let X be a random variable, so be the net gain on a single dollar bet on red. Okay, and this would actually be the same if you were to bet on black because there's the same amount. Because there's an 18 out of 38 chance that the ball lands in a red slot, the probability distribution of X is shown below. So this is kind of like what could happen. Well, you could win a dollar, you could lose a dollar. They're the only two outcomes there. Okay, you're either going to win a dollar or lose a dollar. So there are two outcomes, the sample space and the probability of each outcome. It's right here. So this is where we win a dollar. There's 18 red spots out of 38. And this is where we lose a dollar. So there's the 18 black and then there's the 2 green. So that's why it's 20 out of 38. So that's a probability distribution. And to find the mean, remember we've done this before, just multiply the random variable here. So our number here, -1, times the probability. And again, the -1 is important because that's showing a loss. If we did them both as positive, it would look like the best game in the world, like there's no way you can lose money. So the average in this context is sometimes called the expected value. Okay, it'll be over a long run or many times this game, you can expect to lose this much per game. So let's get back to this. We have -1 times 20 over 38 plus +1, that's our gain, times 18 over 38. If you add all that up, that's exactly how you find the average of a probability distribution. You get -0.05. That's -5 cents. So what that tells us, that is, a player can expect to lose an average of 5 cents per dollar bet if he plays many, many games by betting on red. And you can verify the standard deviation is $1. But again, you won't really have to find standard deviations much. Player only plays a few games, the net gain. So that's what we're talking about. In the short term, it's hard to predict. Like, sure, it's almost 50-50, a little worse that you get red. Okay, but you might win the first 10 rolls in a row. Okay. It doesn't mean you're going to lose the next one or it's going to be black or green. Remember, okay, the wheel has no memory. That's why it says in over many, many times of this game. Okay. So in the short term, hard to predict, but over time, more predictable. So now, come back. Transforming a random variable. Okay, and that means manipulating it, adding something to it or subtracting. So if we look here, I really wish I would stop doing that. Chapter 2, we studied the effects of transformations on shape, center, and spread. Okay. Quantitative data. So that's where we had our graph. And if we added a number to it, it would, move up the number line. If we subtracted a number to it, it would move down, but it wouldn't change the shape or anything. Okay, so adding or subtracting a constant, adding the same positive number A to or subtracting from each observation. Okay, so add or subtract to measures of center and location, being the mean, the median, quartiles, and percentiles. So let's say we had a test where the average was a 70. If I add 2 points to everyone's grade, well, the mean will now be 2 points higher. Okay, the median will be 2 points higher. The quartiles will be 2 points higher. The percentiles will be 2 points higher. So our average would go from a 70 to a 72. Sometimes you'll have a teacher that does that. They'll say, all our tests are on a curve. Okay, we're going to set it so the average is like an 80 or the average is a 70. So if the actual average when they took it was a 68, well, they're going to add 2 points to everyone's grade to make the average a 70. That's how sometimes curves work. Does not change the measure of variability. Okay, so your range doesn't change the range, doesn't change the interquartile range, doesn't change the standard deviation. So it doesn't change any of those measures of spread, and it does not change the shape. All it does, if this is our graph, add 2 points, boom, moves everything up. Subtract 10 points, boom, slides it down. Doesn't change the shape or anything. But if you multiply or divide it, some different things happen. So if you were to multiply a number by, multiply a probability distribution or all the possible outcomes by some number, like let's say we played some Who Wants to Be a Millionaire game and I had all the different amounts you could win. Okay. Well, if I were to like add $100 to everyone's prize, it just takes all my distribution and shifts it up. But let's say I multiplied everyone's prize by 2. That changes things. The person that won maybe $50,000 is pumped up. Well, now they're winning $100,000. The person that won $100 is only winning $200 now with that multiplication. So it's a little different than the adding. And all it does, so if you're multiplying or dividing a number, you multiply that by your measure of center. Okay, the mean, median, mode, you just multiply it by that number. For your measures of variability, okay, you multiply or divide it by that number. So the measures of variability do change, okay? And we're going to do examples with this. But it still does not change the shape. It kind of spreads it out more. It stretches it, but it doesn't change the overall shape. If it were symmetric and, two-peaked, it's still going to have that. So let's look at an example. We actually used this example before. There we go. I did it again. Let's return to a familiar setting. It was Pete and his Jeep tours. Okay, so he's got to have 2 passengers for the trip to run. That holds up to 6, and Pete charges $150 per passenger. So here's your 2-passenger price, 3, 4, 5, and 6-passenger prices, and the probabilities based on, in his experience. And there's your distribution. Okay, so we're going to manipulate it somehow. We're going to transform it. So, and again, we can get an average and everything. So if you wanted the average of this distribution, multiply each random variable up here by its probability. So multiply, add all that up. That's your average. Standard deviation is a little more complex, but like I said, it's very unlikely you'll have to find standard deviation. And you can look back in section 6.1 if you need to know how to do that. But here it just gives it to us. So the average is $562.50 with a standard deviation of $163.46. 46. So if you had to describe that distribution, shape, roughly symmetric, single peak, center, that's our average, 562.5. Variability, that's our standard deviation, okay? So again, shape, center, spread, that's what we're looking for, and outliers. But there are none for that. So So here's where we're going to transform it. It costs Pete $100 to buy permits, gas, and a ferry pass for each day trip. So now this is like cutting off of Pete's take here. So instead of him making actually $300 on the 2-person trip, he only makes $200 because he got to pay for this stuff. Instead of $450, it's $350. Instead of $600, it's $500. So what does that do to our distribution? Well, it just shifts it down. Okay. So what's that going to do to our average? Well, it's going to subtract 100 from our average. Exactly what it did. So again, you can verify it by finding your average again, and you'll get exactly $100 less than before. Standard deviation does not change. It didn't change the spread of everything. It just shifted it. Okay, so standard deviation is the exact same, that 163.46, just like we had before, 163.46. But again, it did subtract that number off of our average. Okay, so whatever it took off of each price, it took off of our average. So here's just a little summary of that. effects of adding and subtracting a constant on a probability distribution. Again, if you add the same positive number or subtract from each value of a random variable, here's what happens. Well, you should add or subtract that amount from your measure of center, mean, median, quartiles, percentiles. It will not change your spread, your variability, and will not change your shape. Here's an example. In a large introductory stats class, the score X of a randomly selected student on a test worth 50 points can be modeled by a normal distribution. That's good. With a mean of 35, standard deviation of 5. Fine. Due to a different question on the test, professor decides to add 5 points to each student's score. Okay, I can kind of see where they're going here. Let Y be the scaled test score. So this is like our adjusted score, okay, or the curved scores. Okay, so let Y be the scaled test score of the randomly selected student. Okay, describe the shape, center, and variability. Shape. Well, it's approximately normal. The shape hasn't changed. It told us it was normal before. Center. Okay, well, the only center we have is our mean, which was 35, and they added 5 points to it. So now our center is going to be at 40 points, our average. And variability, adding a number to every score will not change the spread or the variability. Okay, so again, let's think about this. Let's say our range before scores varied from, 20 to 45. Well, now our scores vary from 25 to 50. Same exact difference if we calculate those, so that's why our spread didn't change. Now let's look at multiplying by a certain number. The professor in the preceding example decides to convert a student's scaled test scores to percentages because the test was scored out of 50 points. So the professor multiplies each score by a scaled score by 2 to convert it to a percent score, and multiply it by 2 because it was out of 50 points. That way, like a 40 out of 50 is an 80%, so that gets you your percentage. So that is W equals 2 times Y, because again, our scaled distribution was called Y. It was this random variable. So now our double scaled distribution is going to be called W. Fine. Okay, so figure 6.3 displays the probability distributions of random variables W and Y. So this first curve, normal, peak in the middle, slopes out each direction, symmetric about the mean, and then this other graph is going to be our doubled or our percentages. So it's still normal distribution, okay, it's still symmetric, but our average is doubled. Standard deviation is now doubled, okay? So yeah, so again, for Y, again, average was 40, standard deviation is 5. Well, now that we double all the scores, we're going to double those things. So now the average is an 80 with a variability of 10 points. So 80% and 10 points. Here's a little summary of those rules by multiplying or dividing by a constant. And again, that works if you were dividing. Divide your average, divide your standard deviation. Okay. So, by multiplying or dividing each value of a random variable by the same positive number B, multiplies or divides the measure of center. Multiply or divides the measure of variability, but does not change the shape. You might stretch it out a little, but it does not change the shape. It still could be, symmetric, single peak, double peak, whatever it was. So here's an example for us. El Dorado Community College considers a student to be full-time if he or she is taking between 12 and 18 units or credits. Number of units, X, that a randomly selected student at El Dorado County Community College is taking on fall is shown below. So full-time is between 12 and 18 credits, and here's the probabilities, okay? You can see there's a kind of peaks because you'll assume most classes are 3-credit courses. So your multiples of 3 are going to have higher probabilities here. So 12, 15, and 18 are more likely than the 13, 14, 16, 17. So there they all are. So if you have to make a histogram or distribution, it's just a bar graph. You have your random variables on the bottom and your probabilities going up top on the vertical axis. So average 14.65 units or credits, standard deviation 2.056. Okay, at El Dorado County Community College, the tuition for full-time students is $50 per unit or per credit. Okay, so remember up here, this is the average amount of credits the student's taking times $50 per credit is where I think we're going. That is, if T equals tuition charge for randomly selected full-time student, T equals 50X. So we're multiplying each number of credits by 50 to get the price. So our new distribution is going to be in terms of dollars. So A, what's the shape does the probability distribution T have? Well, same shape as the probability distribution of x. Okay, it's roughly symmetric with 3 peaks. Okay, because again, this is x up here, right? This distribution, so there's x, number of units. So our new one with number of, or how much the cost is going to be, it's going to be the same shape. Okay, roughly symmetric. Okay, we got a peak in the middle, kind of goes a little hook there up to a peak at the end, and they're same at the top. So it is roughly symmetric with our 3 peaks. Boom, boom, boom. Part B, find the mean of t. Well, we knew the mean before was 14.65, and we multiplied every score by 50 for $50, or every amount of credits by 50. So we're going to do 14.65 times 50. Boom. Our new average, or our average cost, is $732.5, or $732.50. So if they multiply each person's credit amounts by 50, we have to multiply the average by 50, or take a new average, which would be more time consuming and pointless. Part C, calculate the standard deviation. Well, since we knew our old standard deviation of 2.056, we can just multiply that by 50 as well. So that's 102.8, or $102.80. So multiplying by a constant doesn't change the shape, even if it spreads it out a little more. How does multiplying by a constant affect the variance? If you remember, the variance is a stepping stone on the way to standard deviation. Okay, you take the square root of the variance, and that's your standard deviation. So what happens to that? Again, you won't really have to do this, but if you read through here, the variance for that distribution would have been 4.2275. Okay, so the square, okay, the variance of our new distribution, okay, you got to multiply that by 50. Well, not really. You have to actually square the 50 because we kind of have to undo it. Multiply it by that. So you see where they're going here. So there's 2,500 times the old variance, and we had to do it times 2,500 because, again, we kind of had to undo the square rooting. Sorry, I'm just watching the baby over there out of the corner of my eye. He's roaming around in his little bassinet. So anyway, so here's how they found it. 2,500 times the old variance, and the 2,500 is there because we had to do 50 squared to put it back in terms of variance. Because remember, square root of the variance is standard deviation. Okay, so whereas standard deviation we multiply by 50, the variance, we have to kind of go back a step, square that, and then multiply it. But again, that's just kind of a side note. Check your understanding. Okay, large auto dealership keeps track of sales made during each other day. Okay. Let X be the number of cars sold during the first hour of business. So we're looking at the first hour the place is open and the number of cars people sell. So it looks like they sell anywhere between 0 and 3. Okay, and here's the likelihood of selling 0 cars, selling 1 car, 2 cars, 3 cars. So 30%, 40%, 20%, and 10%. So the random variable X, they're telling us the average, which they typically will, 1.1, and again, that's just by multiplying 0 times 0.3 plus 1 times 0.4 plus 2 times 0.2 plus 3 times 0.1. So that's where that 1.1 comes from. So the average amount of cars sold in the first hour is 1.1. Standard deviation, a little more lengthy to find, but they give it to us. It's 0.943. So suppose the dealership's manager receives a $500 bonus from the company for each car sold. All right, so I'm thinking that we're going to be adding money. Okay. So let Y be, the random variable Y be the bonus received from each car sales during the first hour. Okay. So sketch a graph of the probability distribution of X and a separate graph with probability distribution for Y. So X is going to be as is here. Okay, but Y is going to be with our $500 bonus. Now, I have that somewhere. Well, I had it somewhere. Well, let's pull it back up. Sorry for the delay here. Oh, baby's got the hiccups. There's the old check your understanding. Come on. So here's our distribution for X with the number of cars sold, 0, 1, 2, or 3, and the probabilities. Got my mean, standard deviation because they gave it to me. And again, that was called X. So I have the mean of X, standard deviation of X. Now Y, Okay, we're essentially going to we're multiplying by everything by 500. So 0 cars, well, you're not getting any more bonus. Okay, 1 car is $500 bonus, 2 cars is $1,000 bonus, 3 cars is $1,500 bonus. So we multiplied everything by 500. So there's our distribution. You could either get $0, $500, 100, 1,000, or 1,500. Okay, so again, that's just the bonus multiplied by the number of cars because it's 500 per car. Number 2, find the mean of y. Okay, well, we knew the average of x, which was that 1.1. So to get the average of y, we're just going to multiply that by 500. 500 times 1.1 is $550. Part 3 is find the standard deviation of y. Well, again, we knew the standard deviation of x was 0.943. So standard deviation of y, we're going to multiply it by 500. You get 471.5 or $471.50. And last thing here, number 4, we got to see what number 4 says. So we have kind of a new little wrinkle. The manager spends $75 to provide coffee and donuts. Okay, so the manager is now spending $75, so that has to come out of that bonus, right? So describe the shape, center, and variability. So we are basically going to subtract 75 from everything. So shape is the same, okay? But your average is now knocked down $75. So it's down to 475 from the 550. And your spread will be the same because, again, that doesn't change when you are adding or subtracting. All right, so again, read through that if you need to. Okay, and our last little snafu is here. What if we have to do both, add and subtract? 1 second. Got to go check on the kid. And we're back. And hey, baby's here. You want to come say hi? There's Roman. Yeah, he's not too happy, so we're going to wrap this up. But putting it all together, if we have to add, subtract, and multiply, okay, add or subtract and multiply or divide. So we're doing 2 things now, okay? And we're going to use the Fahrenheit to Celsius calculation, all right? So here we have 1 brand of baby bathtub. How convenient. Seems like all these problems are about babies. By the way, we mentioned in the other section about APGAR scores. Roman's score was a 9 out of 10. Very good. Okay, so 1 brand of baby bathtub comes with a dial to set the water temperature. Okay, when the baby's safe. 1 moment, I'm going to pause. Take care. We're back again, so you can see what my past few days has been like. Okay, so here we are. Just need a little pacifier. So we have a normal distribution, okay, with our temperatures with a mean of 34 degrees Celsius, standard deviation of 2 degrees Celsius. Let Y be the temperature, water temperature in degrees Fahrenheit. So, okay, so here's our calculation. Switch it, 9/5 C plus 32. So we're multiplying it by a number and we're adding a number. Well, find the mean. Okay, so to do the mean, remember, we had an average in Celsius and standard deviation. So to do the mean of it, we are going to basically plug it into this formula. We're going to multiply it by a constant and add it. So our mean was 34, so we're going to plug a 34 in here. So we're going to do 9/5 times 34 plus 32. Get an average of 93.2 degrees Fahrenheit. That seems warm to me, but hey, whatever. I guess not. You go in pools when they're, 70, 80 degrees, I suppose. So that's all you do. Okay, so for the mean, you just multiply, add it by whatever you have to. Okay, standard deviation is a little different because remember, adding or subtracting a constant doesn't affect the standard deviation. So all you have to worry about is the multiplying portion of the 9/5, okay? So all you have to do for your standard deviation is multiply by 9/5. So our standard deviation was 2, so we're going to do 9/5 times 2 and get 3.6 degrees Fahrenheit. So just remember, adding or subtracting a constant does not affect the standard deviation, but it does affect the mean, okay? And multiplying or dividing a number affects both. And here just goes into one of the problems, again, that we've done before. If we have a normal curve and you want the probability between this and this, using our mean and standard deviation, you can do it 2 ways with the z-scores, or we can use our calculators and do, the normal CDF, lower, upper, mean, standard deviation. Okay, so guys, that's a wrap on 6.2, part 1. I want you guys to try questions at the end of section number 37, 39, 41, 43, 47. Okay, so end of the section 37, 39, 41, 43, 47. That's a wrap. Have a nice day. Roman, say goodbye. He said, see you. All right. Questions, let me know.